Okay, in this subsection we're going to talk about norm, and norm is very closely related to inner product, as we will see. Norm geometrically means something like length, and if you think of vectors in 3 dimensions, that is, real vectors in 3 dimensions, then the norm is exactly the length of the vector. So this is a generalization of length to any number of dimensions and also to complex vectors. Okay, so let's go to the definition. The definition of the norm of a vector. Now, hopefully this looks to you like the Pythagorean theorem, only with more components. Right, this says the length of u, the norm of u, is the square root of the sum of the squares of the components. Okay, so let's go, here's an example. Here we have u with 4 components. So to find the norm, we take the square root of the sum, 4 terms here, of the squares of the absolute values of the components. Right. I was not clear about that up here, but for complex numbers you have to take the absolute value before you square. Okay, so you need to compute the absolute value of the complex number. What's the absolute value squared of this complex number? Well, there's a formula for that. If you have a complex number z, and the absolute value of z squared is equal to z times the complex conjugate of z. If you have a complex number a plus bi and you take the absolute value of that squared, it's equal to a squared plus b squared. And in fact, these two are equal. And you can show that. All right? So if I take the norm of this complex number 3 plus 2i, I could write that as 3 plus 2i times 3 minus 2i. And if I did that, I would come up with, if I take the first, it's going to be 9. If I take the last, it's going to be minus 4 times I squared, which is plus 4. And then if I take the imaginary part, I'm going to get plus, I'll get minus 6i, and then I'll get plus 6i, and that gives me 13. Now I could have instantaneously gotten that simply by taking 3 squared plus 2 squared. And you can see in this case that if I compute the absolute value this way as the number times its conjugate, that's the same thing as taking the real part of the number, squaring it, plus the imaginary part of the number, squaring it. Okay, so this absolute value of 3 plus 2i squared is 3 squared plus 2 squared. In this case, 1 minus 6i squared, the absolute value of this is going to be 1 plus 36. In this case, it's going to be 2 squared, which is 4, plus 4 squared, which is 16. In this case, it's going to be 2 squared, which is 4, plus 1 squared, which is 1. Okay, you add all these numbers up together, you get this, and you get this. You take the square root, you get square root of 75, which simplifies to 5 square roots of 3. Now, when the vector is real, it's a little bit easier. You just take the square root of the sums of the squares of the components of the vector. So this is 3 squared plus minus 1 squared plus 2 squared plus 4 squared plus minus 3 squared. Work it out, and you get this result. Okay. Right, now, here's a relationship between norm and inner product. The norm squared is equal to the inner product of u with itself. And here you just do by algebra, basically. This is the definition of norm, the square root of the sum of the squares. If you square that, you'll get the sum of the squares of the components. Okay. But as we had up here, this is just using this same fact that I mentioned here, that the norm of a complex number squared is equal to the complex number times its complex conjugate. Okay, so we have this relationship between the norm squared and the inner product of u with itself. Okay. From this we can see that this theorem, actually this comes from a geometrical idea that the length of a vector always has to be bigger than 0, or if the vector is the 0 vector, the length is equal to 0. Okay, so that's what this says. The inner product of a vector with itself is always bigger than or equal to 0, and it's equal to 0 if and only if the vector is equal to 0. Okay? So the proof simply shows that if I take the inner product of u with itself, I get the sums of the squares, of some of the absolute value squares of the entries of u, in accordance with this theorem. All right? Now, if these are not all 0, then this sum cannot be 0. If even one of these is not 0, then the sum is not 0. Okay, so that's what that's saying, is that this sum here is 0 if and only if all of the u's are 0. Okay? So that's basically what this theorem says. You work it both ways. If all of the u's are 0, then certainly this is equal to 0. If even one of the u's is not 0, then the sum is not 0. Okay, and let me stop here. I'll make a separate video for this last section.